should move on to the last talk of the session, which will be given by Emilia Morosan from Rice. And she will tell us about real and reciprocal space topology and square net European EuM4 compounds.
Hi, everybody. Let me see if my computer will cooperate. Please let me know if you can see my slides.
It's the other, this is the presenter view.
Okay. Is this working now?
Yes, I think it was there. And then
I'm going to try it again.
do this swap again. You can swap display or something.
Does this work?
I think so. That's great. Okay. Good.
Right, great. Sorry about that. I've only been doing this for what, 2 years now, and I still can't get it right. So any day now. So I'm not here to tell you about how to use your Zoom skills in PowerPoint, but rather what we find to be a very interesting story of binodal rings and large magnetoresistance in European gallium-4. And I have to thank EuM because I probably could cut about half of the introduction of my slides thanks to the great job that he did with introducing square net band structure and how they play into this nodal ring story. So first I have to acknowledge the funding for this. And more importantly, I have to acknowledge the people that have contributed to this. And I apologize in case I've missed anybody, but the primary work behind the story that I want to tell you today is that of Dr. Ximing Li, a research scientist in my group, with a lot of contributions from Jaime and Kevin, graduate students in my group. And I'll just do a shout out to Jaime, the newly appointed anointed doctor who is now looking for a postdoc. So look out for him. And I'm sure that he's going to be doing great stuff in the future. All right, so let's move on then. And this is an overview, or if you want, a look back of how we ended up with today's story of European gallium-4. That's part of a bigger story that spans the entire gallium to aluminum series in this series of compounds, where several years ago, a previous student in my group synthesized not only the end compounds, the pure europium gallium-4 and europium aluminum-4 compounds, but also the europium gallium-2 aluminum-2, which you can think of as a 50-50 dilution between the gallium and aluminum on the sites shown in this crystal structure on the left in blue and green. However, for the particular mixture of gallium and aluminum at exactly the 50-50, this crystal structure orders. So we don't have just a solid solution between aluminum and gallium, but for this particular case, the aluminum and gallium is actually split on these two sublattices, both of which are square net sublattices. And that's very important for what's happening in europium gallium-4 and across the series in terms of real and reciprocal space topology. And this slide summarizes not just our work, but rather a lot of the recent work on europium aluminum-4, where skyrmion state has been observed at some finite field in the field versus temperature phase diagram that looks like this, multiple phase transitions, very complex, perhaps surprisingly, in a europium 2+ compound. So unlike the compound that Jorn had referred to, which was 3+ here, europium is a 2+ and is magnetic, but you wouldn't expect a lot of anisotropy, and therefore you wouldn't expect such complex magnetism, given that europium 2+ has a half-full electronic F shell. However, if we now move across the series to the europium gallium-2 aluminum-2, notice that the phase diagram is equally complex, and through magnetotransport measurements, detailed Hall effect analysis, we find a complex topological Hall with the maximum at some intermediate field over here that corresponds to this intermediate phase, which we call A. And all of our experiments and analysis point to the fact that this might be a skyrmion state similar to that in the aluminum compound, or at a minimum, a non-coplanar magnetic state in this europium gallium-2 aluminum-2. Contrast this with the gallium end compound in the series, where the phase diagram is much simpler. There's only one phase transition to a in-plane ferromagnetic state with antiferromagnetically stacked planes along the c-axis, as shown in here. However, this very simple H versus T phase diagram might lead you to think that not much is going on in europium gallium-4. But as soon as we look at the magnetotransport, we have the first indication that the story is more complicated than just a look at the magnetic properties. So let's focus on europium gallium-4 for today. This is a summary of what I advertised happening in this europium gallium-2 aluminum-2. And this is a story that maybe some of you recall I told last year at one of these workshops. I'm not going to dwell on what happens in terms of the anomalous Hall effect across the series, although this is a summary of some very recent work which we are about to submit. And for today, the focus is going to be really on this europium gallium-4 and the appearance of Weil nodal rings and large magnetoresistance, as illustrated in this phase diagram. And now I'm going to go in details over a few key points, the centrosymmetric square net and how it plays into the occurrence of these binodal rings. And like I said, I have very little to add to what Jorn had already said, so that will serve me well in delving very quickly into the data, which will hopefully allow me to convince you that we observe topological nodal rings. And we have evidence that's supported by experiment, ARPES, and theory, DFT calculations. In addition, we have quantum oscillation data that is also in agreement with all of the previous, all of these data and experiments. More importantly, one of the things that I've alluded to already is that we also see large non-saturating magnetoresistance in excess of 10 to the 5% at some high field, as I'm going to show you in a little bit. And for a long time, we couldn't quite understand the connection between the Weil nodal rings and this very large non-saturating magnetoresistance. And theory colleagues here at Rice, Matthew Foster and his students, have developed a semi-classical and a quantum mechanical model that actually account for this large magnetoresistance. So let's start with just a little bit of a bird's eye view in these nodal line systems and derivatives. These are the different flavors that one can expect depending on the symmetry, the crystallographic symmetry, and depending on whether either inversion symmetry or time reversal symmetry are broken. We're going to focus on what happens when mirror symmetry is preserved, but either inversion symmetry or time reversal symmetry are broken. And in that scenario, nodal rings can occur. And as Jorn had mentioned, one of the properties of these nodal rings is the non-trivial Berry phase. So one such example of a Weil nodal line that occurs with broken inversion symmetry is in platinum tantalum diselenide. Here's the crystal structure that shows the lack of inversion in this crystal structure. And notice here the band structure calculations and the details of the band structure without and with spin orbit coupling, where a couple of nodal rings occur due to the preserved mirror symmetry. Similarly, if time reversal is broken in this Heusler alloy cobalt-2 manganese gallium, And here's the crystal structure for this compound. In that case, the Weil fermions occur due to the magnetic order in this compound with mirror symmetry, the preserved mirror symmetry. So these are a couple of studies which focused on this compound, showing these Weil nodal lines in the topological magnet cobalt to manganese gallium. However, what I want to tell you about is how this square net in europium gallium-4 leads us to Weil nodal rings. And you've already seen this band structure earlier. I'm just going to point out that in this schematic square net, the dark cell corresponds in my compound to one of the metal sites, gallium-1, and then the light one is the gallium-2 site in europium gallium-4. And you remember the consequence of folding the band structure is that several crossings occur, and they can occur at the Fermi surface when the band structure looks as shown here in the bottom. And that seems to be the case in europium gallium-4, where not only do we have the square net that gives rise to these spinless nodal rings. In the case of just a simple square net, you would expect spinless nodal rings. But if you introduce magnetic order and a spin polarized magnetic state or ferromagnetic state, then what you get is a series of two sets of spinful nodal rings. And when spin-orbit coupling is added in the presence of mirror protection, then these four spinful nodal rings split into two topological nodal rings, as shown here schematically. And we believe that this is what's at play in europium gallium-4 at high fields or fields in excess of 7 Tesla, where we do reach the saturated paramagnetic state or a spin polarized state. In this case, what was an in-plane spin orientation in zero field or in the antiferromagnetic state ends up now being a state where all the spins follow the field when the field is applied along the c direction, as shown here. A reminder of what the phase diagram looks like. Here's the antiferromagnetic phase boundary as a function of field and temperature. And here's the spin polarized state, which I'm going to focus on. In which case, there are two types of spin Dirac nodal rings, or two types of Dirac points. Three of them, the ones shown in blue, that occur in the absence of spin orbit coupling. And the difference between the blue and the red ones are the occurrence on or off the mirror invariant planes. So when we now look at the different pockets of the Fermi surface, there are three sets of Fermi pockets, the ones that are represented here that are denoted as alpha, beta ones, and then two different pockets that we refer to as gamma. So now we want to look at a comparison between the DFT calculation that gives us these Fermi surface pockets. Here, by the way, is just a cross section of this beta pocket, which shows the cutoff in the Fermi surface plane. So we want to compare what happens or what we get from these DFT calculations with experiments. And so this is just a preamble to showing some ARPAS data. What I want to emphasize is that we're focusing on the paramagnetic state, or in the absence of spin orbit coupling, this band structure, where with spin orbit coupling in the ferromagnetic state, we see the three sets of Weil nodal rings who are schematically represented over here. And these are guaranteed by the band crossings in the presence of mirror symmetry. where one particular set of Weyl nodal rings has very low energy variation. This is confirmed, or all of these is confirmed by the ARPES data. As you can see here, we see the different sets of nodal rings, either as we look along path 1 or path 2. And in particular, the one corresponding to this path 2, the YZ path, as shown in this figure over here, is very close to the Fermi energy with low energy variation. And this is consistent with the theoretical prediction based on this toy model of a square net sublattice, which is what we see in European gallium-4. More than beyond the ARPES data, we have compared our DFT calculations with quantum oscillation measurements. And here's the quantum oscillation measurements in one particular case for different angles of the applied magnetic field. And this is the frequency versus angle phase diagram, which showed the evolution of the bands as a function of angle or of the Fermi surface cross section. So what you see is yes, I should have shown how the field is applied. So the field is applied in the AC plane, and remember that the magnetization is saturated along the C direction in this schematic. So when we map the calculations onto these quantum oscillation data, we find for most of the bands very good agreement. And here's that same contour plot from before with the data from quantum oscillations now. And we see very good agreement between these data and calculations. And so together we have good agreement between the ARPES data and the quantum oscillations and the predictions based on DFT calculations for this compound. But in addition to these observations, our magnetotransport measurements, in addition to the quantum oscillations, our magnetotransport measurements have also revealed very large magnetoresistance. And here's just a measurement at the low temperature, 1.8 Kelvin, up to 14 Tesla, with the dark shading here corresponding to the saturated paramagnetic state, where you can notice a number of things. One, that at low fields, the magnetoresistance is quadratic, but it deviates from this quadratic field dependence as it approaches the magnetic ordering transition at about 7 Tesla. And even with the largest magnetic fields that I'm showing in this measurement, the magnetoresistance continues to increase in a non-quadratic manner, and it doesn't saturate. And so that bears the question of what's the mechanism between such a large magnetoresistance. And even further, is there any connection between the Weyl nodal lines and this non-saturating magnetoresistance? So here's that data again, compared also with the data up to 40 Tesla, where you can see that the magnetoresistance continues to increase. And if we estimate the magnetoresistance by calibrating with the low field data shown here, then we estimate that the magnetoresistance altogether exceeds something like 2 times to 10 to the 5th% up to this 40 Tesla value. And when compared with all the other large magnetoresistance compounds, which can be classified in 3 categories: paramagnetic, ferromagnetic, and antiferromagnetic, notice that the largest magnetoresistance seems to prevail in paramagnetic systems, with 1 or 2 orders of magnitude lower magnetoresistance in most magnetic topological systems. However, European gallium-4 seems to stand out as not only the largest magnetoresistance compound in this magnetic systems, but also comparatively large with that of the paramagnetic systems. So if we try to look deeper into an explanation for this magnetotransport properties, a semi-classical model shown here on the left, together with the quantum mechanical model, which is what I'm showing you here on the right, show there are details which I'm not going to go into here, primarily because I would hope that my theory colleagues can explain this better than I can. But what you can observe is that calculations for just a binodal ring system show this quadratic behavior or dependence of the magnetoresistance at low field in both these models, and non-saturating. Furthermore, the quantum mechanical model shows these quantum oscillations in high field or as the system enters the quantum regime. So it would appear that there's a direct explanation for the magnetoresistance or the large magnetoresistance that we see in Europium gallium-4 coming from a pretty straightforward calculation in either a semi-classical or quantum mechanical scenario, each with their own advantages, and with the quantum mechanical calculation additionally showing the behavior in relation with the quantum regime. So I'm going to summarize and maybe take some questions, but the key points that I want to leave you with in regards to Europium gallium-4 and the square net lattice with mirror protection, with spin orbit coupling, and ferromagnetic or saturated paramagnetic state is that Europium gallium-4 appears to be a new topological semi-metal to host binodal ring states. And our experiments and calculations have not only explained the fermiology of this material, but identified 3 groups of Fermi surface pockets that are associated with the 3 different sets of nodal rings observed in this compound. And their signature of Landau quantization and magnetotransfer properties reaching the Landau quantized regime in this binodal ring semi-metal. Jorn talked about the topological phase transition as induced with a structural change upon doping in lanthanum, antimony, tellurium. Here we can hint to a topological phase transition induced by the change in the direction of the magnetic field. It's a little harder to see that from what I've shown you today, but I will just mention that the saturated paramagnetic state can be reached, and the mirror protection is preserved if the field is applied along the C direction. And if the field is applied in a different direction, or if we look into the magnetic order state, then we lose that mirror symmetry protection, and therefore topological phase transition can occur. And lastly, I've pointed out to this large magnetoresistance, which is about 10 to the 5th at 14 Tesla, and nearly another order of magnitude increase when the field goes up to 40 Tesla. And non-saturating magnetoresistance, together with the details of the quadratic regime at low fields and the deviations from h squared at higher fields, that can be accounted for in some relatively straightforward models. I'm going to stop here, and I'll be happy to open this for discussion. Thank you.
Thank you very much, Emilia, for this very nice work. Let me pull up the window, see people are raising. Saeed has the first question.
Yes, thank you for the talk. I have a question. Do you know any evidence of charge density wave in this material?
So the slide that I skimmed over, which summarizes some of the properties, let me see if I can go there. So the short answer is that at ambient pressure, there is no charge density wave in Europium gallium-4, unlike what happens in the rest of the series. So in Europium aluminum-4, there's a charge density wave, as you can see here. In Europium gallium-2, aluminum-2, there is a charge density wave. There's no charge density wave at ambient pressure in Europium gallium-4. You can induce that with pressure, but that's not what we did here.
Mm-hmm. Thank you.
Thank you. Any other questions? Shimel has a question.
Yeah, so great results, Emilia. So just in the spirit of discussion, it's more of a question for both Emilia and EuM. Structurally, is there some degree of differences between the two types of materials, the European gallium-4 and these 111s? It's an ignorant theorist question.
Oh, so the structure is different. The European gallium-4 has two gallium sides, which are both square nets, and they both then contribute to the PX-PY crossing, as EuM very nicely explained earlier on, as I only alluded to with this band structure here. So I think that in the 111 compound, there's a single square net compound, but EuM can correct me if I'm wrong.
Yes, that's right.
Primarily the biggest difference between the two.
I suppose they are in different space groups.
They are in different space groups. Yeah, they are. The 111 is non-centrosymmetric. This 1 to 2 is centrosymmetric. I didn't emphasize this enough, but this is a centrosymmetric crystal structure, which is one of the surprising elements of how the topological properties occur in this structure.
Okay, thank you.
I see JP has a question in the chat. I can read it out for you. How important is the European magnetism for band structure in MR, say as compared to similar results on barium aluminum 4?
Yeah, thanks, JP. So the magnetism here is key to producing these vile nodal rings, as if you follow this sequence of excuse me just 1 second. Yeah, so if you follow this sequence of the toy model of all of a sudden my mouse stopped working now. So not only I had some Zoom issues in the beginning, but now it seems like my computer doesn't like me at all. Well, so I'm going to try to explain it while I troubleshoot my computer. I don't know if it's, I'll blame it on the Zoom. The magnetism provides this saturated or the spin polarized state, which breaks the or produces these spin-full nodal rings, which you wouldn't have in barium aluminum 4. The structure, of course, is very similar, but that's how these vile nodal rings come about in magnetic European compound compared to barium aluminum 4.
Thank you. Yeah. That's okay. Great. Okay. If there are no more questions, I thank Emilia again and all 4 speakers in the session. And unfortunately we ran through all the discussion time left. Exactly. So Shimel and Andrea, how do you want to proceed? Want to have a
Well, probably we should close the session and resume at 1 o'clock.
Which is 3 o'clock in Houston. Yeah.
3 o'clock your time, 1 o'clock our time. Yeah.
Thank you.
So we can give people a break. Well, thanks so much, everyone. For
Thank you,
the great
Emi,
talk.
for running. Yeah.
Thank you.
Thanks to everybody.
Okay, see you later.
Yeah, bye.